In this video, we're going to complete the Kuta software Infinite Algebra 2 free worksheet Probability with Combinatorics. Before we dive in, let's go over our two important formulas. First, we have in CR. This is our combinations formula. In choosing R. Out of a total of n samples, selecting R is going to be n factorial all over R factorial times n minus R factorial. The combinations are used when order doesn't matter. Next, permutations in PR. That's going to be n factorial all over n minus R factorial. This is used when order does matter. So let's go ahead and find the probability of each of the following events. Let's look at problem 1. Number 1 states that Beth and Shayna each purchased one raffle ticket. If a total of 11 raffle tickets are sold and 2 winners will be selected, what is the probability that both Beth and Shayna win? So in order to create a probability, we're going to need to have our fraction out of the total number of outcomes. So the total number of outcomes, if there's 11 raffle tickets and we're selecting 2 winners, order is not going to matter here. So this is going to be 11C2 in our denominator. That's the total number of ways we can pick 2 winners out of 11 raffle tickets. Now we want to know the probability that both Beth and Shayna win. Well, if each of them has a single ticket, that's both of their tickets selecting both of them. 2 choose 2. So our probability is going to be calculated by 2 choose 2 over 11 choose 2, both of those combinations. Our numerator is equal to 1. Our denominator is going to be, let's go ahead and use this formula up here, 11 factorial all over 2 factorial times 11 minus 2 factorial. And I'm just going to simplify quickly because 11 minus 2 is equal to 9. Now I have 1 still in my numerator, and in my denominator, let's go ahead and simplify this down a bit. Notice that my biggest factorial in the denominator of my denominator is 9. So I just need to rewrite 11 factorial until I get to 9, and then I can cancel it out. So I'm going to have 11 times 10 times, let's go ahead and stop at 9, factorial. Because remember, that's going to cancel out with the factorial in my bottom. 9 factorial cancels out with 9 factorial. 2 factorial is just 2 times 1, which is 2. So if we take 10 and divide it by 2, that's a 5. So I have 1 over 55. Then if we convert that fraction into a decimal and then into a percent, our probability is going to be approximately 1.818% for number 1. 1.8% chance of both Beth and Shayna winning the raffle. Let's move on to number 2. Number 2 states that a meeting takes place between a diplomat and 14 government officials. However, 4 of the officials are actually spies. So if the diplomat gives secret information to 10 of the attendees at random, what is the probability that no secret information was given to the spies? Let's start out by calculating the total outcome. The diplomat is giving secret to 10 of the attendees. So out of the total of 14, the diplomat is choosing 10 to tell the secret to. So that's going to be, well, a combination because the order in which he tells the attendees doesn't matter. So we're going to have 14 choose 10 as our denominator, and now we need to decide how to get our probability. We want to calculate the probability that no secret information was given to the spies. So out of the 10 attendees that are told the information, we want all 10 of them not to be spies. So this is going to be 10 choose 10. 10 choose 10 is just 1 all over. Let's work out this combination. That's going to be 14 factorial all over 10 factorial times 14 minus 10 that factorial. Simplifying down, I know that 14 minus 10 is simply 4. So I have 14 factorial over 10 factorial times 4 factorial dividing my 1. Simplifying this down, I'm going to have 1 all over our greatest factorial in the denominator of our denominator is currently 10. So I'm going to write out this 14 factorial until I get to 10. So that's going to be 14 times 13 times 12 times 11 times, and I'll stop at 10 because the 10 factorial will get canceled out. And 4 factorial, I'll quickly write out as 4 times 3 times 2 times 1. 10 factorial, canceling out with 10 factorial. I no longer have a factorial in my problem. And look what else we can simplify down. 4 times 3 is 12, so I'll cancel out this 12. And 14 divided by 2 is 7. So this all simplifies down to 1 over 7 times 13 times 11, which is equal to 1001. So this is 1 all over 1001, which written as a percent is approximately 0.1%. So the diplomat has a 0.1% chance that no information is given to a spy. Moving on to number 3, we have that a fair coin is flipped 10 times. What's the probability of the coin landing heads up exactly 6 times? Well, first let's start off with the total number of outcomes of flipping a coin. Each coin flip has 2 separate outcomes. If we're flipping it a total of 10 times, that's 2 to the 10th. So there's 2 to the 10th different possible ways of flipping a coin 10 times. What we want though is the probability of that coin landing heads up exactly 6. So exactly 6 times it lands on heads. That's out of the 10 times we flip it, we're choosing 6 of those times that it's heads. So that's 10, choose 6. We want to select 6 of those times that it's heads. So that's 10, choose 6. 10, choose 6 is equal to 210, and 2 to the 10th is equal to 1024. Notice that both are divisible by 2. 210 simplifies down to 105, and simplifies down to 512. So 105 out of 512 is approximately 20.508%. Let's move on to number 4. For number 4, we have that a 6-sided die is rolled 6 times. What is the probability that the die will show an even number exactly 2 times? Let's first figure out the total number of possibilities. But think about it. If we're trying to calculate the probability that an even number occurs exactly 2 times, then I don't necessarily care about all the sides of the die. I care about just odd sides versus even sides. So on a 6-sided die, you can see that I have a group of odds, which is 3 sides of the die, and a group of evens, which is 3 other sides of the die. So let's just split this problem into 2 groups as opposed to working with all 6 faces. So for our total number or our total outcomes, we're going to do odd versus even. So when you roll a die, you're either going to get an odd side or you're going to get an even side. So there's 2 possible outcomes when rolling that die. And how many times were we rolling it? A total of 6. So that's 2 to the 6 different outcomes when rolling a die, where those outcomes are based on odd and even. What we want to do is find the probability that the die will show an even number exactly 2 times. So out of 6 rolls, we want 2 that are even. So that's going to be 6, C2, a combination, since order doesn't really matter. Calculating this out, that's going to be 15. And 2 to the 6th is 64. So our probability, when converted to a percent, is 23.438%. Let's move on to number 5. For number 5, we have a test that consists of 9 true-false questions. A student who forgot to study guesses randomly on every question. What's the probability that the student answers at least 2 questions correctly? First of all, how many different outcomes are there? Well, if there's 9 questions and it's true-false questions, there's 2 different outcomes for each 9 question. So that's going to be 2 to the 9th different outcomes. What we're trying to figure out is the probability that the student answers at least 2 questions correctly. So answering exactly 2 questions correctly would be, out of those 9 questions, selecting 2. 9 choose 2. But this isn't exactly 2 questions. This is at least 2 questions. So we also have to calculate the probability that, if it's at least 2, we have the probability that they get exactly 2. We need to add that to the probability that they get exactly 3. And then exactly 4. And so on, all the way up till they get all 9 correct. Because they're getting at least 2. Now, I don't know about you, but this is a lot of calculation to do. Let's simplify this down. Because remember, probabilities sum to 1. So if this is the probability they get at least 2 correct, all we need to do is take 1, since probabilities sum to 1, and subtract the probability that the student gets less than 2 questions correct, which is only the student getting 1 correct or the student getting 0 correct. And again, that's out of 2 to the 9th different possible outcomes. So calculating 2 of these is a lot easier than calculating for choosing 2, 3, 4, 5, 6, 7, 8, and 9. We can simply just do it for 0 and 1, and that's going to be the probability that the student doesn't get at least 2 questions correct. So we have to subtract that from 1 to get what our true question's asking. So this is going to be 1 minus 9 choose 1 is going to be 9 over 2 to the 9th, which is 512. And then 9 choose 0 is going to be 1 over 2 to the 9th, which is 512. So we have 1 minus 9 over 512 plus 1 over 512. That's 1 minus 10 over 512, which may be a little hard to see. So let's write this that whole number, as 512 over 512. Now when we do the subtraction, we'll get 512 minus 10, which is 502, all over 512. Both of those are divisible by 2, so let's simplify that fraction down into 251 over 256. And that is, as a probability, in percent form, 98.047%. Let's move on to number 6. For number 6, we have that a basketball player has a 50% chance of making each free throw. What is the probability that the player makes at least 11 out of the 12 free throws? So because the player has a 50% chance of making each free throw, think back to flipping heads or tails. 50% chance they miss or make it is similar to flipping a coin and getting heads or tails. So we just need to calculate the total number of outcomes for the 12 free throws. So if it's either a hit or miss each time, that's going to be 2 to the 12th of those total possible outcomes. Now we're trying to calculate the probability that the player makes at least 11 out of 12. So at least 11 out of 12 is, out of those 12, choosing 11. Order for this doesn't really matter. It doesn't say that they can't miss the second shot. It's just 11 out of the 12. But we're going to have to add that too because it's at least. That calculates the probability of getting exactly 11. We also need to calculate the probability of getting exactly 12 and sum that together. 12 choose 11 is going to be 12, and we're adding that to 12 choose 12, which is 1, and that's all over 2 to the 12th. This is going to give us 13 all over 4,096 And when written out as a probability, that's approximately 0.317% chance. So the player has less than 1% chance of making at least 11 of those free throws. So with that being said, let's move on to the next page. This problem states that a technician is launching fireworks near the end of a show. Of the remaining 14 fireworks, so let's start underlining things. There are 14 fireworks left, 9 of them are blue, and 5 of them are red. If she launches 6 of them in random order, so she's launching 6 of them, what's the probability that exactly 4 of them are blue ones? So out of the 14 fireworks, we're launching 6. So the total outcome is going to be 14, and we're choosing 6. And the order doesn't necessarily matter. So 14C6 is going to be our denominator. Now we want to find the probability that exactly 4 of them are blue ones. So exactly 4 is out of those 9 blue, selecting 4. So that's 9, choose 4. However, we have an issue here. If we want exactly 4 and we've only specified that we're choosing 4, what about the other 2? The other 2 out of our total of 6 have to be red. So not only do we have 9 choose 4, we need to multiply that by 5 choose 2. Because getting exactly 4 of them blue, we also need to get exactly 2 of them as red. So calculating this out, 9 choose 4 is going to be 126, and that's going to get multiplied by 5 choose 2, which is 10, and that's all over 14 choose 6, which is 3,003. 126 times 10 equals 1,260, and that's all over 3,003. And when we divide that out, we're going to get approximately 41.958%. So the technician, she has a 41.958% chance of choosing exactly 4 blue. Number 8 states that a jar contains 10 black buttons and 6 brown buttons. So we have a total of 10 plus 6. That's 16 total buttons. If 9 buttons are picked at random, what is the probability that exactly 5 of them are black? So this problem is similar to that last one, where think about it. If we're choosing 9 buttons and they're asking us only about 5 of them, there's 4 that are unaccounted for. And if we want an exact color, then the other 4 need to be the other color. So let's dive in. Again, out of those total of 16, we're selecting 9. And order doesn't really matter. So 16, choosing 9. How many black buttons do we want? 5 black buttons. So out of the 10 total black buttons, we're choosing 5 of them, but we need to multiply that by, out of the 6 brown buttons, we need to choose 4 of them. Because that 5 plus 4 is going to give us 9, let's go ahead and calculate this out. 10 choose 5 is 252, and that gets multiplied by 6 choose 4, which is 15, and that's all divided by 16 choose 9, which equals 11,440. 252 times 15 is equal to 3,780. And when we divide that by 11,440, what we get is approximately 33.04%. So this is approximately equal to 33.042%. Let's move on to number 9. Number 9 says that you're dealt 5 cards from a standard and shuffled deck of playing cards. Note that a standard deck has 52 cards and 4 of those are kings. And again, we're being dealt 5 cards. What's the probability that you'll have at most 3 kings in your hand? So out of the 52 cards, we're dealt 5. So we know our denominator is going to be 52 choose 5. We're trying to calculate the probability that you'll have at most 3 kings in your hand. Now think about having at most 3 kings. That would be calculating 0, 1, 2, and 3. But why don't we just negate this? Because remember, if we calculate the probability that we have more than 3 kings, we can subtract that from 1 to get the probability that's asked. So we're going to do 1 minus the probability that we have more than 3 kings. So we're going to do 1 minus, well, the total outcome, 52, dealing 5 cards, that's 52, choose 5. That's the total number of ways to deal 5 cards out of a 52 deck. And if we were trying to calculate the probability that we'll have at most 3 kings, we're going to do 1 minus the probability that we have more than 3 kings, which is going to be getting dealt all 4 kings, and then out of the 48 that aren't kings, because out of the total of 52, there's 48 that aren't kings, we also still need to have one of those in our hand. So that's getting dealt all 4 kings and one of those cards not being a king. That's going to be equal to 1 minus 4 choose 4 is 1 times 48 choose 1. That's going to be 48 all over 52 choose 5 is a whopping 2,598,960 different ways of getting dealt 5 cards. So when we work out the math, doing 1 minus 48 over 2,598,960, we're going to get approximately 99.998%. So the probability that you will have at most 3 kings is 99.998%. So that's less than a 1% chance that you're going to get dealt all 4 kings. Let's move on to our last problem, number 10. If you've been finding this video helpful, please feel free to give me a thumbs up. Just go ahead and click that like button. But let's continue on and finish this out. We have that a bag contains 6 real diamonds and 5 fake diamonds. If 6 diamonds are picked from the bag at random, what's the probability that at most 4 of them are real? Well, let's start off by figuring out how many diamonds are in the bag total. 6 real plus 5 fake, that's 11 total diamonds in that bag. And how many are we choosing? We're choosing 6 out of that bag. So out of the bag of 11 diamonds, we're selecting 6. And again, there's no replacement. Things are being drawn at random. Order doesn't matter. So 11, choose 6. Now it states, what is the probability that at most 4 of them are real? This is similar to that last problem we just did, where we had at most 3 kings. So as opposed to figuring out that at most 4 of them are real, let's take our total probability of 1 and then subtract the probability that more than 4 of them are real, which is, well, 5 of them are real, or all 6 are real. So out of the 6 real diamonds, we choose 5 of them, and that means that we're choosing 1 fake diamond, so 5 choose 1, and we're going to add that to, out of the 6, we choose all 6, and that gets multiplied by 5 of the fake diamonds, choosing 0. Working this out, we'll have 1 minus 6 choose 5 is 6, times 5 choose 1 is 5, plus 6 choose 6 is 1, times 5 choose 0 is 1, and that's all over 11 choose 6, which gives us 462. So we have 1 minus 6 times 5 is 30, plus 1, so that's 31 over 462. 1 minus 31 over 462 is going to be 431 over 462, because 462 over 462, if we take away 31 over 462 from that, we get 431 over 462, which, written as a percent, is approximately 93.29%. So 93.29% chance that when picking 6 diamonds out of the 11, at most 4 of them are real. And with that, we wrap up this worksheet on probability with combinatorics. If you have any questions, please feel free to leave them in the comments below. And as always, don't forget to like, subscribe, and share.